In this short series of videos, we're going to be expanding upon KSP calculations and looking at the different types of calculations that you can do with KSP from most elementary to most complicated, starting with actually calculating KSP itself. So in our first example, we're told that a solution that has a precipitate of barium fluoride present contains specific concentrations of each ion of which the precipitate forms. And from this, because we know that we're at solubility equilibrium, because we have a saturated solution that has a visible precipitate, we can calculate KSP. So in order to do this, the only thing that we really need is to make sure that our KSP formula is correct, and so we can write out our dissociation precipitation equilibrium with barium fluoride in equilibrium with one barium ion and two fluoride ions like this, meaning that our KSP formula is going to be the concentration of barium 2 plus times the concentration of fluoride squared, again compensating for the coefficient of 2 here. And then all that we need to do is simply take each of our concentrations and put them directly into the formula for KSP. And if you calculate this correctly, you should find that the KSP of barium fluoride comes to approximately 1.84 times 10 to the negative 7. Now, once again, the only part where this calculation can possibly go wrong is likely in the writing of the KSP formula itself, and the only two things to keep in mind are, number one, that the concentration of the solid form of the solute doesn't appear in the formula because the concentration of solids is constant, making sure that each ion has the appropriate exponent based on the coefficients in the reaction. So if we take a look at example 2, this actually looks on the surface fairly similar to a molar solubility calculation, and it actually is. So in this case, we're not calculating for KSP, but we're calculating what the equilibrium concentration of one of our component ions is when a precipitate just begins to form, and this wording here is a tip-off that this is talking about the point where we hit the saturation point, implying that this is the point at which solubility equilibrium is established here. So even before we figure out what our KSP value is, we can look at this reaction and the formation of the equilibrium. So in this situation, when a precipitate just begins to form, implies that we do not start at equilibrium, and since we aren't given any initial measurements to the concentrations, we can assume that both of these are zero, meaning that magnesium hydroxide is being formed in pure water, which means that our equilibrium can only move to the products like this because there is no precipitation reaction if we don't have either of the ions. Now, if we use the equation to look at our stoichiometric ratios, we see that the ratio is 1 to 1 to 2, meaning that the magnitude and direction of change for each ion are going to be plus x and plus 2x, meaning that if we want to calculate the concentration of magnesium ions, we're going to be solving for x rather than 2x. Now, when it comes to writing the KSP formula, again, this is pretty much exactly the same as in example number 1. We have concentration of magnesium 2 plus times the concentration of hydroxide with a squared exponent corresponding to the coefficient of 2 here. Now, since we don't have concentrations for these, we're actually going to input x as the concentration of magnesium and 2x as the concentration of hydroxide. But before that, in order to solve for each of these, we actually need a value for KSP. So if we check our data table, we can see that the KSP for magnesium hydroxide is 5.6 times 10 to the negative 12. So if we go back here, we know that our KSP is equal to 5.6 times 10 to the negative 12, which is going to be equal to x, the concentration of magnesium, times 2x squared, the concentration of OH minus squared. And if we expand all of this out here, 2 squared is 2 and x squared is x squared, and then 2 squared is not 2, 2 squared is 4, and x squared is x squared. So 4x squared times x would be 4x cubed, which means that in order to solve for x, we need to divide both sides by 4 and then take the cube root of whatever that we get. So if we write out what x is, it would be equal to 5.6 times 10 to the negative 12 divided by 4, and then if we take the cube root of both sides, that would be how we cancel the x cubed from this side here. And since we know that that x is equal to the concentration of magnesium, when we put this into our calculator, that means that we have calculated the moles of Mg2 plus per liter. But of course, this question isn't done, which is why I'm not going to bother rounding this number here, because we need to use this in the follow-up calculation here. So after we find what the ion concentration of Mg2 plus is at equilibrium, here the question is asking what is the maximum amount of MgOH2 that can dissolve in 250 milliliters of solution. Now here, you would think that we would need to go back and calculate what the molar solubility is in order to do this, but we actually already know it. Because the mole ratio of our solute is equal to the number of moles of Mg2+, that means that our concentration of Mg2+ is also equal to the molar solubility. In other words, the moles of MgOH2 per liter that actually dissolves, which means that we can just take the value of x and apply our calculations to this. So we know that x is equal to the cube root of our KSP, 5.6 times 10 to the negative 12 divided by 4 moles of MgOH2 per liter. And if we want to find the maximum mass of this that's able to dissolve in a specific volume, we need to multiply by the volume here. Of course, we need to change these units to liters, so 250 milliliters is the same thing as 0.2500 liters. So this tells us the amount of moles of our solute that are able to be dissolved. And if we want to convert to mass, we would need to find the molar mass. And for those that don't know offhand, molar mass of magnesium is 24.31. Molar mass of oxygen is 16. 16 times 2 is 32. Molar mass of hydrogen is 1.01. 1.01 times 2 is 2.02. So if we work through some quick arithmetic here, our molar mass of magnesium hydroxide is 58.33 grams per mole. And if we check our units, we see that grams is the only unit we have left, which means that this calculation should lead us to the maximum mass of our solute that can dissolve. And if we put this into our calculator, this comes to approximately 1.6 times 10 to the negative 3 grams of magnesium hydroxide that can be dissolved. In the video that follows this up, we're going to take a look at a situation that is similar to the calculation we did here, where we want to calculate the concentration of ions that can dissolve in pure water, only we're going to look at how to do this calculation assuming that our water is not a pure sample.